Welcome to the second module of the training. In this module, we'll create a shellcode and inject it into another process. We'll use the following tools. The first one will be Ali Debugger, which we'll use to create a shellcode and check the course of the program execution. The next tool is Visual Studio, using which we'll compile our program. But first of all, let's answer the question, why do we actually have to write shellcode? We create it in order to inject it into the process. We'll benefit from that a bit. In this case, we'll just want to close the process, but this time from the inside. The moment we inject the shellcode, the program will close itself. This way, we'll avoid a situation when another program, for instance an antivirus, makes it impossible to close the application from the outside. As a result, the program we'll inject the shellcode into will close itself. Now let's spare a moment to think about what our shellcode will look like. The task of our shellcode will be to execute the ZW-terminate process function, which closes the process. It takes two parameters. The first one is the process handle, the second one being the process exit code. We give 0 as an exit code. That's the neutral exit code without an error. We just put 0 on the stack. The next parameter is -1. It's a pseudo handle for the current process, returned by the getCurrentProcess function. Next, we call the ZW-terminate process function. The next instruction is ret. It won't be executed anyway because the process will already have been closed by then. The term function has the following form. It consists of a shift of 101 hexadecimal value to the EAX register. It's a number of our syscall, and it's different for each system version. 101 corresponds to the ZW-terminate process number for Windows XP. We work on the Windows 7 system, and this value will be set dynamically for our version of the operating system. Further, we can see the call of the keyFastSystemCall function. However, we don't call this function from the library. We created our own code, which looks identical to the code present in the NTDLL library. Let's start from creating our shellcode. We'll open a notepad in Ali Debugger. It's just our draft code. Let's write our instructions here. Push 0. Push -1. Next, we'll call the term function. So it will be call, plus 5 bytes from this place, that is 00193692. We've forgotten about the ret instruction. Let's change our value to 93 because the ret instruction takes up 1 byte. Another issue is entering the syscall number, that is MOV EAX 101. What follows is the call of the sys function, so we have to update our address one more time. It will be 0019369D. Another instruction is MOV EDX ESP, followed by the sys enter and ret. Looks like our shellcode is ready. We just have to copy it. We can do so by pressing the right mouse button, choosing binary, and then binary copy. Now we can save it somewhere else. Here we have a ready program where we placed our shellcode earlier. But let's see how to do it right from the start. We paste our code and replace spaces with \x in the selected part. We can see that the code looks virtually the same. When writing, we omitted one ret call after call sys, but it makes no difference because it won't be executed anyway. our shellcode is now ready to work. In the shellcode size variable, we can find the shellcode size. The variable syscall number offset includes an address, that is, the place in our shellcode which has to be modified in order to update the syscall number. In the comment, we get the same, but saved as an assembler code. The kill app function kills an application using our shellcode. It assumes the process number as a parameter. Let's check which process number to get. As we can see, the function creates a buffer and copies the shellcode to it. Let's keep in mind that we also have to get the syscall number. As we've already seen, the ZW-terminate process function is composed of mov EAX101 and a call. Mov EAX101 is 5 bytes long, where the first byte tells us which instruction it is, and the 4 remaining ones include the 101 number. Thus, in order to get the syscall number for our system, we get the second byte from the beginning of the address of the ZW-terminate process function and copy it to our code, increasing the value by 0b, which makes it exactly the 11th byte. Once our shellcode is ready to be injected, we use OpenProcess with permissions to operate on virtual memory, with rights to write and create new threads. It will enable us to close the process from the inside. Next, we use the virtual allocx function, which allocates 32 bytes of memory, or if you prefer, 20 in hexadecimal notation. We save our 32 bytes using the function writeProcessMemory under the address returned by virtual allocx. We provide the buffer with the shellcode and enter the code size as the next parameter. Using the createRemoteThread function, we start a new thread which will be executed in the context of the process we want to close. We can see that as the code beginning we provided an address where we saved it to the memory. Now we just need to close the handle. The main function looks as follows. It checks whether a parameter was provided. If that's the case, it changes this parameter to a number using the a to I function and passes this number to the program. Now let's compile our program and see what it looks like in the debugger. We close this debugger instance and start a new Notepad instance. We see that the notepad is already running. Now we need its process number. We enter the task list command, which gets the process list. But we want to get only the processes which have a string notepad.exe in their name. We can see that the process number is 644. We have to remember this value. Now we open the program we've just created. However, this time it's open in Ollie. We have to provide its call parameter. As we remember, the number of our process is 644. As we've already learned, what we see now is the compiler prologue. Let's go through it. First we press F8, then F7. We go a bit lower and see the main function. We press F4 and F7 to step inside. That's our code. The standard creation of a frame takes place by using the push EBP instruction, and next, move EBP ESP. Then in EBP +8, there's a number of parameters passed to the program. We can see that we compare it with the value of 2, which is precisely the value we have in the program. We can see here how this instruction is written in our program. We press F8 and see that the jump is performed, which means that the parameter was passed. We press F7 to jump. Next, from the address specified by the EBP +C, the value is copied to the EDX register. It's a data buffer. Next, the value from the address indicated by EDX +4 is copied to the EAX register. That's the 644 string, exactly what we passed to the program. We use the A2I function to change it to an integer. It's exactly 284 in the hexadecimal notation. We can check it for ourselves. Next, our function is called. We jump inside by pressing F7. Actually, it's all we've seen in Visual Studio. Let's go through a couple of these instructions. getModuleHandle gets a handle of the NTDLL module. That's the base module address. Next, we get an address of ZWTerminate process. It's present in EAX. Now let's see what this function looks like inside. We press Ctrl-G and simply step inside EAX. We see mov EAX and the number of our syscall. In our system, it's 172. Next, there's a call of the function, the address of which can be found under 7FF E0300. It's the address of the KeyFastSystem call function. Let's check what the function looks like. We see that it's exactly what we've implemented in the shell code. Let's return to our code. The syscall number was copied from the address of function +1, that is, from EAX +1. We can see that in the EAX register, we have the value 172, which equals the syscall number in our system. Now let's open the process we want to close. We see that everything executed correctly, and we have a process handle in EAX. If the execution failed, we would see here only the letters F, which means that there is a failure. Now we have the code responsible for allocating memory. We press F8 so as not to step inside the function. We can see that the function returns the address of the allocated memory. It's 001D0000. In the next step, we have to save the code to this address. We see that we entered the 001D0000 address. Our buffer with the code, and the size of the buffer, that's 32. We press F8 so as not to enter inside. Now we place a breakpoint in the place we saved the code. Let's check whether the memory is allocated. We see that's the case. Let's return to our code. We press Ctrl G and enter the value 001D0000. It's exactly the same code we've already seen. We press F2 to place a breakpoint and return to our application code. A new thread will be created now. We press F8 and our thread starts. We can see that the debugger stopped at the defined breakpoint, which means that the execution of the code we injected took place. Let's see this code. We press F8. There appeared the value 0 on the stack. That is the exit code. Then we see -1. That's the value returned by getCurrentProcess. In order to prove that this value is returned, let's check the function code. We see that the FF, 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 FF value is added to the EAX register. As a result of this operation, we always get -1, regardless of what was earlier in the EAX register. We put it on the stack and call the code from the address 001D000A. We press F7. The 172 value will be placed in the EAX register. And next, the code from this address is called. We press F7 one more time. The program will be closed now. We press F7 in order to execute the sysenter instruction. We can see that the program closed and exited with code 0. Everything went as expected. That's all when it comes to this module. We've managed to create our own shellcode, inject it into the process, and close it. This skill will be useful further in the training. See you in the next module.